we are going to talk about how to use the machine learning for the analysis of the data in electron microscopy. Now, one very important thing now is that when we started to work in this field, or us and several other groups 20 years ago, the situation was that at that time we had the data. We barely had the computational capabilities to store the data because the analyzing the even relatively modest EELS data set on the desktop PC at that time was a problem. So remember that cloud computing exists for less than 20 years. So 20 years ago, it was lugging the hard drives and analyzing them on the desktop, unless you manage to have your own HPC around. And also at that time, the ecosystem for the code analysis was fairly limited. So you either have the certain amount of the analysis function in Python or MATLAB or R or Eager or whatever, or there is not much you can do. So starting from about 10 years ago, it was the problem of the reaches. So the data sets generated by microscopy actually didn't increase that much. However, analyzing them was fairly straightforward. So the code was out there, the way to store the data was out there, so it was not a big deal at that time. What was the limiting factor is knowing how to code and knowing what to code. So unless you know Python and unless you spend considerable amount of time and effort learning how to use it, there is not much you can accomplish. So for the last 3 years, courtesy of Sam Altman and all the people who work on the coder assistance and large language models, we have generally both the computer wherewithals and writing fairly sophisticated code is not a problem. You can easily take a data set, EELS data set from computer, from your microscope, import it in the Colab, use the ChatGPT to write code that will analyze it any way you want, formulate a prompt about what you want to be output and what is the formatting for the output you want to get, and the ChatGPT will do it, and it will work. So the key thing, however, is how do you develop the logic and intuition that is required to analyze the data in a way that is meaningful and brings some sort of value. So what I'm going to try to do today is to illustrate the logic of the analysis of the data. And as Gerd mentioned, one of the most important things in any field is knowing what is that you have to know. So he calls it a dictionary. Since I'm coming much more closer to the machine learning field, I call it the operational semantics and ontology. But the idea is exactly the same. So you need to know what is that you have to know. Another thing is that, as you can imagine, I spend considerable amount of time using ChatGPT for pretty much everything that I'm doing. And I started to use the large language models from the moment when the Galactica came out. And then, of course, Meta got cold feet and pulled it out. And then ChatGPT came, and then OpenAI came out with the ChatGPT 3 weeks later. So there are certain things that large language models can be doing, and there are certain things large language models cannot be doing. So if you have a question and you know how to ask a question, the LLM probably would be able to answer it for you. So the two cases when the LLMs are fairly useless or dangerous are the cases when you don't ask the question. So the LLM will not necessarily see the problems that you would do. And second thing is that keep in mind that LLMs tend to trivialize things. So if you ask a question and you have a feeling that it answers the question that is slightly different from what you have in mind, that probably means that you are up to something new and it's really worth going in that direction. If the LLM gives you the answer which matches your expectation and sounds clear and kind of explains the detail, that means that you personally don't know this thing, but it's generally well known, and that's opportunity for learning, but not necessarily for scientific R&D. So in these two lectures, so one would be about the linear methods, Another would be about the VAEs. We are going to try to focus on the philosophy of the data analysis and the hyperspectral imaging and look at several examples of the analysis techniques. So the first important thing is that why do we use linear methods? So we have all kind of the unique machine learning methods, VIEs, foundational models, what's not. Why would we use the linear models? And the answer is very straightforward, that there is a physical principle that if the solution exists and it's unique, it doesn't matter how you find it. So in the field of differential equations, guessing the solution is the well-established tradition, because if you guess the solution, then you know that it's only one and it's unique. So in many cases, when we deal with the physical systems, and especially with the hyperspectral imaging, whether it is EEL, EDX, and so on, the solution is linear. So the signal is the linear combination of the signals of the individual components. If the physics of our process is linear, using the nonlinear models is not justified. It's actually a very bad idea. So, and as I said, many of the practical microscopy methods that we have are in fact linear. So what's very important is that if we have a finite spatial resolution, that typically means that our signal is convoluted with some probe function in the XY plane. So convolution doesn't change the linearity. So the convolution of linear signals in the XY is also linear. So this being said, both today and several days in the previous days, you saw many examples of the spectroscopic imaging, meaning that you typically have XY plane, and then at each point you have a spectrum in the energy direction. So notice that the diffraction, when you come by the like 4D stem, when you get the diffraction pattern at each point on the image, technically is also the same thing, except that at each point you have not one-dimensional spectrum, but two-dimensional spectrum. So overall, this structure, so XY plane in which you do sampling, typically on the rectangular grid, and then at each point you measure some spectral data set, is absolutely common for most imaging methods, whether it is STEM, SPM, and so on and so forth. So typically what we want to do with this type of data sets is to get some materials insights. So there are two ways how we can do that. So one is if we have a physical model. So if we have a physical model, we want to extract the relevant parameters from data, and they will directly have the physical meaning because we already have the model, and model has meaningful parameters. The problem can be that the model can be imperfect. For example, we don't have the very good model for low loss EELs, even though we have a pretty good models for core loss or for EDS. So this is called the epistemic uncertainty. If our model doesn't fit the data generation process, that's kind of called the epistemic issue. So our data can be noisy. That brings the aleatoric uncertainty. So the good thing is that our analysis results generally don't really depend on the sampling of data in the XY. So the physical models work as they are. They don't care about how much different behaviors are present in the XY plane. So if we don't have physical model, we can use the intrinsic structure of data through the unsupervised learning based on the data only, or supervised learning, so meaning that we have some form of correlative model trained on previous examples that we apply to the new one. So there are good things and bad things about these approaches. So in the unsupervised learning based on the data only, so it sort of looks for internal structure of the data, but your analysis results would be very much dependent on the sampling of the points in the XY plane. So if we have some behaviors associated with a small number of defects, the results of the deconvolution would be very different than if these defects occupy a big part of the image plane. Another very important thing is that we always think that unsupervised and supervised methods don't depend on physics. That's not true, because any machine learning methods is predicated on some fundamental definition, like definition of distance between the instances of data. It's just how we do things. Unfortunately, the definition of distance is a physical property. So if we try to do the analysis of the data set where the units are electron volts or vice versa, the wavelengths, the results of the analysis can be subtly different. In most cases, the difference would be minimal, but there are enough cases when it would be tangible. So always think about the format of the data, always think about what is your x-axis, because practically that matters, and any textbook in machine learning will basically not tell you that. That's the difference between physics and ML. The third very important thing is that as I mentioned, I worked on machine learning and physical sciences for 20 years. So if there is a single most important message that I want you to know is that the best machine learning is physics. We use machine learning if we don't know physical models well enough. We use machine learning if we need to make decisions fast and we don't have time to invoke the physical method. But ultimately, always physics first, machine learning second. So the good thing is that a lot of things in machine learning and physics would be almost the same in terms of the analysis, but what's different is the interpretation. So physical models have meaning and they're explainable. Machine learning models can be made explainable if you spend enough time and effort. So going back to the linear methods, the most general form of the analysis of the spectroscopic data set is what is called the general linear unmixing. So what it practically means that we have our three-dimensional data set, which is the signal as the function of x and y and as a function of energy. So in this case, x is energy and r is the xy. No, vice versa. Sorry, x is the spatial variable and r is our vector parameter. So we start with this three-dimensional data set. What we want to do is to represent it as the linear combination of weights and members. So the weights form the spatial maps. So instead of three-dimensional image, we get multiple two-dimensional images. And the components is basically the behaviors that correspond to each loading map. So basically the loading map and the component go in pairs, and they make sense only as a pair. So this one allows you to expect the physics, and this one shows you how the corresponding physics is distributed in the XY plane. Now, what's very important is that this type of linear methods don't start with the machine learning. They start with the things such as the linear regression. So linear regression methods or multiple linear regression methods basically say that, look, I measure the unknown signal, and I know that this unknown signal is the linear combination of some sort of other signals with the unknown coefficients. But at the same time, the functional form of the signals itself is known. So in some sense, it is just a linear fit problem. It's not anything related to the machine learning at all. So the question becomes, where would you take this type of known end members? It can be from the manual, so it can be the reference, standard reference. In some cases, you can just get them directly from the data. So this is the example of the EELS data set for the strontium titanate, lanthanum, strontium manganite, bismuth ferrite interfaces. So we have a three-dimensional EELS data set across this region. We want to answer a question whether the physical properties are uniform across the system. How we're going to do that? We make a hypothesis that the properties are uniform within the material, but may change at the interfaces. Then we take the spectra inside the kind of away from the interfaces as the known end members. And then we try to represent all other spectrum as the linear combination of those in the bulk phases plus some error. And then what's very interesting that so once you have three components, it's always convenient to represent the results as the combination of the red, green, and blue. So you can see that if we do this fit and find the fitting map, you can see that we have a fairly uniform fields and we don't have much error signal. If we try to do the same type of analysis in the plasmon energy range, so this is the core loss region. We measure only the core electrons. This is where the plasmons are. You can see that one of these interfaces actually demonstrates significant error signal. So basically, using this method, we kind of demonstrate that as far as chemistry is concerned, everything is linear. And as far as plasmonic properties are concerned, one of the interfaces have the anomaly. Notice that in terms of machine learning, this is almost trivial. But in terms of physics, this is a making hypothesis, going from hypothesis to the simple solution. And then obviously you need to find out why it's happening, but that can be done. So another very strongly very important tenet here is that if you take the classical machine learning courses, or if you have a PhD or attend the courses in the EECS, machine learning community tends to be fixated about using the latest and greatest models. So the foundational model, LLM, diffusion model, whatever. If you want to use machine learning for a real-world problem, your approach has to be exactly opposite. What you have to do is to find the simplest model that still solves the problem. Going for the latest and greatest is very often the road to nowhere. And if you want to rationalize this too, then my advice, think about machine learning as your hobby that you spend several hours a day just to stay current. But use of physics, you always use the simplest thing that you can. Great. Now, speaking about the different scenarios. So, okay, in these cases, I assume that I know where the end members came from. What am I supposed to do if I don't know where the end members come from? And this is the situation which is solved by so-called principal component analysis. So principal component analysis is a very old method. It was invented for the first time around 1850 and formalized in the beginning of the 20th century. Basically, what it says is that I have the unknown signal. I separate it in the product of the loadings and the loading maps and the components, but I don't know either. This is a blind deconvolution problem. So it sounds like a magic. You have a three-dimensional data set, and then you represent it as the pairs of the loading maps and the components, and somehow you get them out from nowhere. So it turns out that the principal component analysis has a very simple logic that the requirement is that the eigenvectors or components are orthonormal. And they're arranged in such a way that the corresponding contributions are planned in the descending order by variance. So in electron microscopy, this method was first time introduced by Noel Barnett around 1990. So Gert probably met him. But it really started to take off only after 2006, so basically 20 years ago. So you may ask the question, why? The answer is very simple, because in 1990, we did not have the computers that allowed to do it, and then 2006, we already had. So what type of information can the PCA give you? So I'm going to show you the examples which come from many fields and not only electron microscopy, primarily because in many other techniques, it's much easier to explain what you're looking at. So imagine that you're taking the STM data set. So here you basically have a data set where you have XY plane, and then you take IV curve and location. How are you going to interpret this? So you can take a cross-section in the XY plane for a fixed energy. It will look very noisy because most of your data lays outside of this region. You can take a cross-section where you move along single line and plot as a function of X and current. So then you can see something like this, but then you lose all the information about what happens in the XY plane. So if you take this three-dimensional data set and dump it in the PCA, you're going to get something like this. So you have a pairs of the components and the corresponding loading maps. And all of a sudden, you start to see things. So some of these things are relevant to materials. So you clearly start to see that there is some anomaly in this image. Some of these components look like noise. So they look like noise here, and they look like noise here. So it turns out that PCA has this wonderful capability that if you have something like 60-cycle noise kind of coming from the electric plugs and so on, it will generally filter it out in the two components, and they would be orthonormal. Now, how do you interpret it? PCA, remember one thing, PCA is exceptionally well defined from the point of view of information theory. PCA generally does not have any physical meaning unless you can specifically prove that it does exist. So typically, once you do the PCA analysis, then you go through multiple iterations saying, look, I see the feature here. This feature exists on the map corresponding to the first PCA component, and this component looks like this kind of parabola. So basically, what it tells me is that in the dark regions, the contribution of this parabola is larger, so notice that it's minus, and in the bright, it's smaller. This component looks like a parabola in the opposite direction, but then there is this offset here. So the region when this component is larger means that this negative thing contribution is stronger as well. So notice that this is not a quantitative discussion, it's heavily qualitative. And all the PCA analysis is like that. This being said, it can be very, very useful. So, for example, very useful in finding the weak behaviors inside the image. So in this case, however, a very important trick is that classically, if you do the PCA, the textbook will tell you that you determine what components matter and what doesn't matter based on this inflection point in the what's called the scree plot, the magnitude of the eigenvalues. So in this case, it looks like 20 components matter and all the rest is noise. It turns out that practically it's also a very good idea to calculate the correlation function in the XY plane. So correlation function in the XY plane shows you whether there is a spatial structure. So you can see that the spatial structure is concentrated in the first several eigenvalues, 8s, 18s, and then 42 and 44. So we would actually throw away 42 and 44 if we use the classical criteria. So always look at the spatial domain and the classical information theory methods. So as I mentioned, PCA generally does not have direct physical meaning. So only in a very few cases it is possible to analyze the data using the normal analysis method like functional fit and by PCA. And in these cases, sometimes it's possible to build a semi-quantitative relationship between the physical descriptors and the PCA components. So most of the time, and as I said, I've done it for 15 years and I taught a very large number of tutorials and courses about it. Plus I worked in the user facility, which means that I dealt with much larger volume of data than is normal. In most cases, the semi-quantitative PCA analysis goes along the lines that we have a component that shows us the peak. We have the components that goes like this. This type of component should be interpreted like a shift of the peak. Sometimes we have a components that look like Mexican hat. This means the change of the width. That's all you can do. If you have the data from two peaks, you can sometimes see whether these shifts are correlated or anti-correlated. But then the things become really complicated really fast. Now, when we talk about the PCA, it's also important to bring up the connection between the PCA and the clustering methods. So, I mean, PCA tries to disassemble your data set in the products of loadings and components. Clustering methods try to basically take your data set and ascribe the label for each instance of the data in the data set. So clustering is super useful. We can apply it for any type of spectral data set quite easily. And typically what we do with the clustering data is that we plot the spatial localization of the labels. So then we kind of get the psychedelic images like this. And for each cluster, we can also find out the what is called the core set or centroid, meaning the characteristic data set within the cluster. So generally, clustering is better justified when we have different behaviors which are substantially different. So within each class, variation is small, but the difference between the classes is large. That's where the clustering is justified. The PCA is justified when the variability is slow. So basically, there are no classes. There is only some smooth factors of variability. And then we do the PCA. So what else is out there? So by now, the collection of the linear analysis methods is it's like a very, very large zoo. A very interesting analysis method is what's called independent component analysis. So what PCA tries to do is try to orthogonal transformation to transform the correlated variables into a set of linear uncorrelated ones. So independent component analysis basically tries to separate the signals into additive subcomponents, assuming they're statistically independent. So the mathematical formulation in this case is exactly the same as the PCA. In fact, one of the things that you can discover is that the mathematical framework for all linear analysis methods, PCA, ICA, factor analysis, NMF, whatever, is pretty much identical. Which means that if you want to use them, you really need to look carefully about what is the physics or what is the inferential bias underpinning the method. In PCA, it is orthogonality of the components. In the ICA, it's statistical independence. In factor analysis or NMF and so on, it would be kind of more complicated. So the typical example, this is kind of how they will look like. So if you have a data set that looks like this, PCA will try to find the factors of variation. So the ICA will try to separate the data based on the non-orthogonality. Practically, ACA works very, very well when we deal with the problems generally known as the cocktail party problem. So imagine that you are in the bar and there is a soccer game on, people talk around you, nonetheless you are somehow capable of listening to the person next to you and kind of filter out everybody else, even though it's louder. So this is what is called cocktail party problem. That's what ICA does remarkably well. So for example, imagine that I create an example when I have three data streams. So one is red, the triangular wave, one is blue, the sine wave, one is green, the square wave. So if so this is my ground truth. My observations are some linear combinations of those. So my observations look like this. If I try to take these observations and separate them using the PCA, I mean, I get some separated components, but these components don't look anything like original the data sources. And if I try to put this type of data in the independent component analysis, then the output is actually magic, because you can see that I perfectly reconstructed the square, sine wave, and the triangular component. Admittedly, they are reconstructed down to the factor of -1, but that's kind of what's the factor of -1 between friends. So in other words, ICA is a very powerful method. It's relatively easy to use. So at this point, everything is easy to use. The caveat with the ICA is that in most cases, for the data sets that we are working with, whether it is EELS or STM or STS, the fundamental assumption of ICA is not fulfilled. So at least in my experience, once we deal with the spectral data or image analysis, it was almost kind of useless. You could get the data, but then it is important to explain what it means. I expect that ICA would be super useful once we analyze the data, which is the sum of multiple sensors which are streaming in time. So if we have the data as the function of time detected from multiple detectors, it would be useful. So anything related to dynamic data, parallel detection, and so on can be super useful. But again, I haven't seen the example of it happening so far. So what else can you do with the linear method? So remember that I said that the primary thing in machine learning is to understand what is the physics behind it, and then using machine learning for analysis of physical data kind of becomes a very interesting process. It's like, imagine that if you remember Shrek when he was talking about the fact that ogres are like onions, right? So think about your data like an onion, and then you try to remove the complexity until something that remains is very, very simple. So the way that you remove the layers of the onion from data is by taking the analysis tools that incorporate some aspect of physics inside it. So it's actually very interesting, and I'll show you the example of this with the variation layout encoder analysis as well. But if you have a data which is high dimensional, so you cannot comprehend it as a human. I mean, we are not good at percepting anything above 2D. If we apply some machine learning method, and if the result of this analysis looks complex, I mean, it can look cool, psychedelic, interesting, colorful, whatever, but if it looks complex, that practically means that we didn't learn much. But if we apply some machine learning methods and the results magically look simple, that actually means that we somehow discovered the right way to represent the data, and that means the right physics. So a simple example. So if you studied courses like chemical kinetics or chemical engineering or whatever, very often you have a curve, right? And then you know that if you plot the curve in certain coordinates and it starts to look like a straight line, that means that you figure out the relevant chemistry. Like if something becomes a line in the log plot, that means that first order reaction kinetic. If something is line in log, it's second order kinetics, and so on. So scientists for kind of practically centuries come up with this idea that if you find the right way to represent the data and it looks simple, that means that you understand the physics behind the data. The same approach works inside for the machine learning methods, except that we no longer have the criteria that we have a straight line. We have kind of look at slightly different things. But the corollary to that is that we need to have methods that allow us to add additional assumptions on the data deconvolution process. So as I mentioned, PCA is the most straightforward one, very powerful tool, very robust, only orthogonality of the components. So there are other methods. So for example, there is a technique called Bayesian linear mixing, which also does the linear deconvolution of the data, but it comes with the constraint that the sum of the loading maps is equal to 1. So very small difference, allegedly kind of very small difference compared to the PCA. However, once we add this type of constraint, this immediately means that this Bayesian linear mixing is ideally applies for the chemometrics problems or problems that are sort of measuring the spectra over the phase diagram, because in phase diagram, by definition, the sum of the components at each point is 1. So this is a very strong example of the physical inferential bias. So let me show you an example of how it works. And this example would apply for atomic force microscopy, but the same logic can be applied to STEM ILS or any other detection techniques. So imagine that we have two materials forming the interpenetrating network. So one material is ferroelectric, another material is not ferroelectric. We also know that the ferroelectric material has a transition from the ferroelectric to non-ferroelectric component at some temperature. So now imagine that we take a Raman spectrum. So Raman spectrum, like think about it like EELS type of information. So it's vibration spectroscopy, but it doesn't quite have the spatial resolution. So we can take this Raman spectra at different temperatures. So we have at low temperature, at higher temperature, at even higher temperature, and so on. There is a problem, however, that the spectrum that we measure is the linear combination of all the phases present in the system. And since we don't have the spatial resolution, we cannot figure out what component belongs to each phase. So in this case, you can see that these are multiple spectra that acquire the different laser powers, and different laser power is essentially the different temperature of the sample surface. So the question is there a way for us somehow to take this spectra, the function of temperature, and separate it in the spectra of the components? It turns out that we can do that. So this is an example, a fairly elegant example of the multimodal imaging. So the first thing that we need to do is we need to establish that our sample undergoes the phase transitions. In this case, we have another microscopy that has high resolution, does not give us any information about the chemistry, but we can use it to prove that the material undergoes phase transition inside the system. And then what we can do is we can take the very low resolution maps of the our system. So we still have some spatial resolution, but very poor one. And then we apply this Bayesian linear unmixing. So we try to separate our data into the certain components and certain fractions. And then all of a sudden you can see that this is how our components look like. So one component just gradually decreases with temperature. Another component clearly goes down. And a third component is zero, and then it kind of appears out of nowhere. So it's very clear that this component is the one that is the paraelectric phase, not ferroelectric phase. This is the ferroelectric phase, and this is the paraelectric phase in which the ferroelectric is converted at high temperature. And then we have the independent separation of these components inside the material. So notice in this case, there is the situation that our data has a very poor quality. It doesn't have spatial resolution. It only has variability from point to point. And we use the right machine learning method that respects the physics of the system. And as the result, we were able to do the blind deconvolution that tells us both the ideal physical behavior and the phase transition. So again, this type of things can work for any spectroscopic signals as long as they're linear. So there can be more complex examples of that. So for example, we can, at least in SPM, we can come up with the more complex spectroscopies, which generate very large volumes of data. It's fairly not straightforward to figure out what that means because this is a 4-dimensional data set, so the data is highly noisy. If we try to look at the averages, we look one thing, but then we lose all the fine details. If we try to look at something like the hysteresis under the curve, we get something noisy as well, so not clear what it is. However, if we apply the same type of Bayesian linear unmixing, we have absolutely perfect data. So we have the 4 components which have a perfect physical sense. So one component is linear, another component is not linear, third component is almost like noise. Notice that here the vertical axis is small. Third component shows the perfect hysteresis. So one very important thing is that when you use any kind of linear unmixing method, always keep in mind whether it does normalization or not, because sometimes the vertical axis matters and sometimes the vertical axis does not matter. But then if we look at the spatial localization of this component, so it kind of becomes kind of really interesting because, for example, these 2 components are conductivity and not hysteretic, but notice that they have a very complex spatial structure. For example, this grain clearly has a core shell structure, and these grains do not. And you can see that the central part of this grain is more nonlinear than the periphery. You can also see that the hysteretic component is sitting only at the boundaries between the 2 phases. So this is pretty much a textbook example of the linear methods giving non-trivial results when applied to complex multidimensional methods where there is not much we can do by the normal approaches. Of course, we can do a next step and try to fit it to physical model, but that's where the things become a little bit more questionable, even though nominally we can do that because our signal generation mechanism is linear, therefore we can interpret the components as well. This being said, I showed you only few examples. So the PCA, the Bayesian unmixing, there are many more. So there is a factor analysis, there is an MF, there is a sparse PCA, which basically means that the number of components at each point has to be minimal. So the good thing is that all of this, there is factor analysis and so on. The good thing is that by now, all of this are present in the scikit-learn. If you want to learn how to use these things, there is no other way but to go to the scikit-learn, go through these functions one-to-one, either by yourself with read the docs or with the ChatGPT. The idea is to understand what is the physical principles behind this type of analytics. So Don't worry about programming. By now, it can be taken care of by the LLMs. Don't worry about the data volumes or whatever, because unless you start to work with some ginormous data sets, we have more than enough computational resources to do that. It is now a given that you can take your data and, using the 10-minute interaction with ChatGPT, analyze it in 20 different ways. In fact, I put a notebook on the course GitHub that shows this analysis for EELs. So those of you that have laptop in front of you can play with it. It kind of practically illustrates how you can analyze it, the data in 20 different ways. What really matters is that the analysis has to be meaningful. We are physicists, we are not data scientists. Using data science and physics start with the physical problem, transforming into the data science domain, and then taking the data out, analysis results out of data science domain based into physics, which means adding meaning to it. So unless you're a domain expert, or unless you really listened to Gerd in the previous 2 days, which makes you a domain expert, or at least a big starter one, you cannot do that. So machine learning doesn't ascribe meaning to the analysis results, only physics does. Now, let me show you a few more things that we can do with the data, because it's kind of useful, and it also illustrates how to use simple tools when the complex tools are available. I mean, first of all, I mean, as you notice, I like to show this picture, which comes from Gatz, Muller, Jones, and Roulet. Yep. So as an early example of the analysis of the yields with the neural data sets. But let me explain to you again the logic of when we will use supervised machine learning methods. So first of all these methods are already not linear. So once we have a neural networks, that's usually not linear decomposition. Secondly, there is a slightly different logic there. So the idea of the neural network is to, or the simplest example of the use of the network is to build the regressor. So regressor means that on the one end, as the feature or input, we have spectra or image patches or diffractions or whatever. As the output, we have the target or label or property that we want to correlate to our spectrum. So, for example, the input, so I show only 2 neurons, but it can be 100. The input can be spectrum. The output can be phase label. If the output is phase label, then we deal with the classification problem. We want to classify our materials based on spectra. So what's the difference between the clustering? Clustering is an unsupervised method. It takes the data and separates in the groups, or which are maximally separated from each other, and then each group comes with the index, meaning the cluster label. The classification problem takes the data, takes the examples of the relationship between the data and some form of label, trains the model to recognize these examples, and then try to expand this to the unknown instances of data. So as the example, you always have to kind of experiment with the, we always need to answer the question, where would the labels come from? So we can do it exactly the same way as we did for the linear methods. Practically, it is a super good idea to, when you have the unknown data set, to always start with the unsupervised analysis. So always start with the PCA and the clustering. And sometimes it gives you the things that are super useful. So this is example of the PCA of the yields on the calcium titanate, strontium titanate data. So you see that several of the components don't show much. In fact, if you look carefully, you will see that they show the noise spikes. And it's also very interesting that another property of PCA is that if you have a small number of noise peaks, each of these noise peaks will kind of grab a PCA component for itself. It's not a good idea to do that because this separation is not clean. So each of these PCA components will also pull a part of the real data, but it's kind of interesting thing. But in this case, it's very clear what the components mean, right? So we have calcium, titanium, and strontium. So here you have a strong component on the left and 0 on the right. Here you have vice versa. So notice that the scales are, this is negative and this is positive. And the third one is present everywhere. So in this case, you can interpret that this component is titanium, this is calcium, and this is strontium. It's very rarely works like this, but sometimes it does. So with the neural networks, if you create the examples of the data and labels, you can basically build a classification problem. So the linear deconvolution neurons would be the same thing as the regression. So it would be the linear separation. The nonlinear one will basically produce the phase labels. So notice that this was done 15 years ago, but if you do it now, the answer would be pretty much the same, except that you can also retrain the model. So I showed you this example of the linear deconvolution. So this is also the case where you can see that there is a difference between the physics and the PCA. So physical analysis gives me an answer that is clearly shows that we have a linear combination of our spectra, and then we have one anomaly. If I try to run the principal component analysis, the number of components becomes very large, and figuring out which ones are correct and which ones are not becomes virtually impossible. So it becomes a case where you have so much data that you get lost into it. At the same time, if you build the classifier, then it becomes kind of questionable. So some of the, depending on how you configure it, you can get the situation when all the components are interpreted, you can get situation when there is some anomaly, and then there is a situation when anomalies are everywhere. So why does it happen? It happens because we took the nonlinear model, and the nonlinear model does not have intrinsic regularization mechanism. So when we do something like this, we use the right model for the right problem. When we use something like this, we use the complex model, and therefore we can kind of overfit, which means that we start to see in the data the things that should not really be there. So that's kind of part of the reason why I say that we should always select the simplest model with the matching physics. So the same type of approaches can work in many other cases. So this is another example when we try to make the comparison between the data in image plane and the data in the spectral plane. So imagine that we have some unknown objects. So in this particular case, these are two different types of bacteria. And what we measure is the spectrum like this. So the equivalent from the STEM ills would be the low-loss ills when we measure the fairly complicated spectra without the clear physical model. So can the machine learning become useful in these cases? The answer is it can. So what we can do is, for example, we don't necessarily understand what the spectra means, but we know that getting the high resolution image takes time and effort. But if we take high resolution image, we can recognize what we are looking at based on shape. But at the same time, we can take very sparse spectral data. So we take very few spectra, we cannot recognize shapes. But the question becomes, can we recognize the objects based on spectra rather than shape? The answer is that yes, we can. We can basically train the neural network based on the spectra using our known segmentation result as label. And once we do that, we can apply it to the whole original data set. And basically, we start to see that based on spectra, for example, this is the same time as bacteria as this one. And here we see that there is a region which shows the same behavior as this bacteria, which was not a part of our training data set. So the idea is that once you deal with the microscopy data set, sometimes we have a lot of information in the XY domain, and we can use this information to form the labels in spectral domain. And then we can use the same type of spectral approach over the much larger domain and identify the unknown objects there. So the idea is that kind of feel free to go forward between the different ways of labeling and different ways to analyze the new data sets. So this was kind of cool example exactly because in this case, the recognition measurements work. Now, the last thing that I want last thing that I want to show you about the spectral data is how can we use the machine learning to connect the spectral data to the theoretical model. So this is very complicated because if we have a good model that can be expressed as the analytical solution, we should just feed the model to the data. If we have the model that does not perfectly fit the data, so what I mean by that is that your model can predict some form of outputs, but these outputs are not exactly the same as experimental data. So in the machine learning language, it's called being out of distribution. So that would be a problem. So in many cases, we can have a situation that when our data is noisy, we can feed the model reasonably well, but the model parameters would be uncertain. So this is the case when we have a large noise level, and therefore we don't see the difference between the data and the model. It may be the case that we get the data which is very clean with very low noise, and then the small difference between the data and the model really throws off our attempts to fit it. So this is the region when the epistemic uncertainty dominates. If something like this happens, you always have to kind of focus on what is that you postulate. For example, you have reasons to believe that the model is correct, and therefore all the deviation of data from the model is something about the non-ideality of your imaging system or what's not. Or you can choose the approach that you absolutely believe the data, and then the comparison between the model predefit and the data basically tells you how well the model captures the data. So you see the difference, right? So remember one thing, that we always have a balance of belief in the data and the model. We can absolutely believe in the data, and then we can try to find the model that fits it better. We can absolutely fit the model and then try to find the way that what's wrong with the data. But we really cannot have absolute belief in data and the model at the same time. So it's either or. Practically, of course, we have a balance of belief, meaning that I don't believe in data and I don't believe in the model, and I can just choose. Notice that the same type of logic applies to no matter what you do with the microscope, because sometimes we take the known sample and use it to calibrate the microscope. In this case, we believe in sample, but we use the belief in sample in order to improve the microscope. And sometimes we have the microscope that we believe it and look at the unknown sample. So obviously, and I will show you an example on Friday when we absolutely believe both in sample and in the microscope, and the predictions are very much not aligned, and then we have to question our understanding of physics. But so science always works in this type of circle between improving the instruments, learning something new, kind of find the finding the disagreement between what we expect and what we measure, improving our models, and so on and so forth. So it's kind of a cyclic process. So anyway, going back to the examples of the models and the neural networks, the question is, can we use this method to feed data to the physical model? The answer is yes. So basically, one of the simplest way to do it, which is a very primitive form of the model calibration, is that we can take a neural network, feed it to the train it using theoretical data, and then apply it to the experimental data. So of course, in order to do that, you need to have a model. So this is the example when the model was a very simple lattice sizing model, which gives you the kind of a lot of hysteresis curves. We can show that the model is capable of self-recognition. So if we train the model using the data, it would be able to apply it to the modeling data that's part of the test data set and would get answers. Interestingly, this type of models show you the capability for interpolation or even interpretation of the structurally different models as the example of the normal model. For example, if I did the fit for the model with a continuous disorder, and then I try to apply the trained model to the data set which is out of distribution and is created for the delta type disorder, it would be able to find the model parameters which are actually fairly reasonable. So it even has some limited interpolation factor. And then if you try to apply it to the experimental data sets, the behavior would be it's plausible, but if you start to do things carefully, you will find out that the answer is very sensitive to the detail of correlation. So you can get an answer, but the answer is not robust. So a very important thing for any type of machine learning analysis is to explore how sensitive is your analysis to the small changes in the way the data was curated. Because physics-based models usually incorporate any type of curation as the part of their structural expression. For example, any kind of difference in the vertical axis would be taken care of by the normalization constant. So physical models have meaning, and usually this meaning combines both the physics itself and the parameters related to the instrument. Machine learning models will behave very differently. So you cannot rely on this type of things. You actually have to check. And sometimes checks tell you that things don't work very well. So let's stop here. And as I mentioned, I have put the notebook with this type of analysis on the school. Let me share it. Today is day 3. Let me share this one. Share. So I put it on the school website. So basically what this notebook will have is the same EELS dataset that had been shown yesterday for EELS dataset on the plasmonic nanoparticles. And you can pick the dataset that you like. So if you like this one, pick this one. If you like this one, pick this one. You can extract the individual spectroscopic curves. And then you basically can experiment with things like Kalinin clustering. You can experiment with the more complex clustering methods like t-SNE or UMAP. You can experiment with trying to use labels for different representations. So basically what you see in this type of graphs is that once you have spectra, you can get labels from one method, for example, Kalin's clustering, but represent them in the different, using different methods, for example, t-SNE. And then you can use the Kalin's clustering in order to color the distribution in the t-SNE or PCA space. The practical usefulness of this approach, I mean, it's not zero, but you need to be very careful about what type of questions that you ask. So what, for example, what is the similarity between the different methods? So you can do things like non-negative matrix factorization, so very useful. You can do things like factor analysis and analyze how the factors mean. You can implement the collection of the methods from NMF, PCA, factor, independent component analysis, sparse PCA, dictionary learning, and so on. So all of these methods give you the outputs that are looking suspiciously similar, so the pair of loading maps and the spectra. So notice that all of them, so this is why I chose this example, notice that all of them will have different distribution of meaningful data. So for example, first component has this type of peak, everything else looks weird. All of them behave slightly differently on how they treat noise. So notice that here, all the components look smooth. Here, some of the components clearly started to pick up this kind of weird patterns due to the aliasing or what's not. So bottom line is that it's kind of exactly what I mentioned, that based on how the loadings and components look, we cannot make any judgment which of these methods is correct. So you always need to make this judgment based on the physics behind the method. And then there are even more complex methods like self-organized feature maps and so on. So kind of play with it. And ultimately, these notebooks, so let's say 5 years ago, this type of notebook would be something that we share because people can take it and apply it for their own data set. So at this point, it's much easier to ask ChatGPT to give you the analysis code just because it's available.